Hi, and welcome to this discussion of wind direction measurements. And we're working our way through wind vanes and how they respond to a change in wind direction over a period of time. This is known as a dynamic response. So in another video, we looked at how a wind vane will respond to a change in wind direction. If there is a step change in wind direction, we saw that the result was a sinusoidal solution to this equation. In other words, what happens is the wind vane will initially change in the direction of the true wind, the new wind direction, but then it overshoots it and continually oscillates about that new wind direction. And the oscillation does not change. In other words, it continues on forever as long as the wind speed and direction is the same. We call this an undamped solution. This is what the undamped solution looks like. The dotted line indicates the change in wind direction, and the red line indicates the response by the wind vane. That's not what really happens. Wind vanes eventually settle down in the direction that the wind is coming from, and they finally stop oscillating about that direction. This is called a damped solution, and there is damping that is built into a wind vane. What we mean by damping is that it eventually the oscillation diminishes over time, and the amplitude of that oscillation gets smaller. So in other words, the oscillations get smaller and smaller until finally there's no oscillations. So what is done with wind vanes is try to incorporate a restoring force that's proportional to the angular speed of the wind vane. The angular speed meaning how fast the wind vane is moving back and forth. So this restoring force is determined by the aerodynamic force and also the speed of the wind. So there are things that we can do with the aerodynamics, meaning that we can lengthen the distance from the center of rotation, in other words, the shaft of the wind vane out to its airfoil, or we can modify the airfoil to create a force that will cause damping. So that's what we're looking at, the solution for this equation. It is now a second order non-homogeneous differential equation because we added a new term that makes it non-homogeneous. For those of you who've had algebra, don't worry about that. But what this means is that the aerodynamic force, the speed of the wind, and also the inertia of the wind vane determines what kind of solution you're going to get. And we can categorize the solution, in other words, we can categorize the response of the wind vane based upon how, of course, it responds into three different categories. One is critically damped, another one is overdamped, and finally the third one is underdamped. Now, these are not strictly just three solutions. These are actually a range of solutions, and where one stops, another one begins is a matter of debate, really. And it all depends on these forces that are causing the damping. So let's go through these three different ones. The first category is one where the wind vane is critically damp, and that's where it responds exponentially to a change in the wind direction. In other words, it doesn't overshoot the true wind direction at all. It slowly responds to the new wind direction. And it doesn't make for a very sensitive wind speed. And I wish I had some animation, but you can think of it as the wind vane slowly turning in the direction of the new wind and never overshooting the direction of the new wind. On a diagram, it looks like this. I have put on here the undamped solution that we talked about already. This is the oscillation about back and forth about the true direction. And now we have a damped solution. This is the critically damped, where it looks like an exponential function where it just slowly responds and eventually gets to the point where the wind speed and the wind vane are the same, pointing in the same direction. So that is your critically damped solution to this equation. There's another solution, another category of solutions, which we call overdamped, and this is where the wind vane responds slower than the critically damped case. And so it's really not something that we want to design our wind vanes to have. This is where you can think of it as it is slower to get in the true wind direction than the critically damped. It doesn't overshoot, but it just really slowly moves in the direction of the new wind. And the green line represents the overdamped. And then finally, our third solution of dampening is the underdamped. And an underdamped is where there is not much damping. And so the wind vane actually overshoots the true position of the wind, the true direction of the wind initially, and you have oscillations about that point until finally each oscillation gets smaller and smaller, and eventually it is pointing in the direction that the wind is coming from. And this is the orange line, and you can see the orange line initially looks similar to the undamped where it overshoots, but then it comes back and eventually does get smaller and smaller oscillations until finally, after a period of time, it settles down to the direction of the wind, the true direction of the wind. So the undamped, believe it or not, the underdamped is preferred over all of the other solutions. So we can think of the damped wavelength as the time for one complete oscillation for the underdamped case. So as I said, we prefer to have wind vanes slightly underdamped. We don't mind them overshooting the true position of the wind. And you've probably seen this before looking at wind vanes. They kind of go back and forth, but each one of their oscillations is smaller and smaller until they're finally pointing in the direction of the wind. And the reason we like to have an underdamped wind vane is because it's more responsive. It responds very quickly. It takes less time to get to the true direction, or at least it overshoots the true direction, but it takes less time to get there. And of course, most wind vanes are underdamped. So those are the three solutions of a wind vane, and as I said, underdamped is preferred. Now we'll look at the distance constant, and this is similar to a distance constant for a cup anemometer, as we discussed before. Distance constant is the product of the wind speed and the time required for a vane to make 63.2% of the change from one direction to another. So it comes back down to the 63.2%. So in other words, your distance constant is, of course, the time that it takes at a particular wind speed or wind velocity. So there's your velocity and time. But it's the time that it takes to get to within 63.2% of the final wind direction. So here are some characteristics that we like to have in a wind vane. Number one, it's nice to have low friction at the pivot point because it swings rather easily. Good static balance, which means that there must be a counterweight on the nose of the wind vane to counteract the weight of the airfoil on the back of the wind vane. It needs to be perfectly vertical. In other words, if the wind vane is at a slight angle, then the weights are going to sling and bias the wind vane to be pointing in one direction. And then finally, we want good torque, good aerodynamic force, or that results in an aerodynamic torque, because then we have a very responsive wind vane. And of course, that tends to overshoot, but because we have dampening, eventually it will dampen and show the true value after a little bit of overshoot. Other favorable characteristics, minimum inertia. This comes down to mass and also the friction of the bearings. You want it to be very responsive. You want it to swing around and also be responsive to any gusts that are occurring. Also, you want a low threshold speed so that it responds to very low wind speeds on the order of 1 knot or about 1/2 meter per second. And also, it has to be rugged enough to withstand hurricane force winds. And we're talking on the order of 180 knots. So there are various different types of wind vanes. The wind vane, the airfoil is popular. So is the other two, the single flat and the flat wedge. So those are the different types of wind vanes and the different responses of wind vanes.